think you're on the air.
Perfect. Thank you. Thank you very much for having me here. It's a really great opportunity. And it's a really nice place, too. So today, I think you've seen a little bit of a preview from what John was talking about. So I'm going to continue to talk about something similar, but in slightly different context. I'm going to talk about stability of periodic traveling waves in the full water wave problem. But I'm going to do it in one dimension. And since Walter's not here, it's OK that I say one dimension. And they clarify it later, and I think nobody will be too upset. All right. So I'm mostly going to focus on results of Deconic and Oliveira's for gravity waves and stability of periodic waves in only in the presence of gravity. I'm also going to talk about results that have a small coefficient of surface tension. And then also more current work where we've increased surface tension, and we're looking at stability results of that. And then acknowledging more funding. All right, so outline. So I'm going to start off with some background, and you guys will know a lot of it, but just so that we're all on the same page, I'm going to just list some of the results that we're assuming are known. And I'm going to talk about reformulation of the water wave problem, the way that we do it, and talk about how we actually compute the solutions. Then I'm going to go on to talk about stability and show some stability results. All right, so hopefully this is OK to see. It looks a little light, but the water wave problem is here. So I think you've all seen this slide or something similar before. I think the main things that I want to point out is that we're periodic in X. We're one-dimensional because it's kind of hard to point from there. We're one-dimensional because we're only going to really compute eta, which is the surface elevation, and it only depends on X, which is the period, and it depends on time. The period we're going to set to be 2 pi, just for simplicity. The other important things are sigma, which is the surface tension, and then g, which is gravity coefficient. Right, so I think I don't have to explain this. Right, so there is a lot of contribution to this field, and so here are some of the pictures. Some of these are older pictures, and some of these are probably newer. I think you ran a marathon or something. I don't know. We're going to pretend it was Palmer. I have no idea. But these are some of the people that have contributed to the full water wave problem. And it's funny, too, because they range from somewhat cartoon representations to more modern pictures that are in color. All right. So there's over 200 years worth of literature. And some seminal results include, well, we know that if we have these Euler's equations, we can construct solutions in the form of a series. And then Stokes also postulated a wave of maximum height. And the existence of that was proven. And then we know that for capillary waves, we can also write down a series solution. And this is done for infinite depth. However, we know that it actually diverges when surface tension parameter is equal to 1 over an integer. And so Wilton was the one who came up with Wilton ripples. And so that's exactly it. So then we also know that the Stokes solution converges in infinite depth for gravity waves, so no surface tension. And that was done by Nekrasov and Levi-Civita. This was extended to finite depth by Struick. And then also, Crapper wrote down an exact solution for capillary waves as a series. All right. So then more modern results. People looked at stability. So there's the Benjamin-Fehr instability for deep waves by Benjamin and Fehr, Whittam. And then we know that in infinitely deep water, people have done numerics. For example, McLean, he showed that there are the gravity waves in deep water, in infinitely deep water, have instabilities. And he actually went on to define 2 cases of these instabilities for odd and even combinations. And then we also, Chen and Safman had work which investigated capillary waves, and so they also found some instabilities. And then Sakharov went on to show that Euler's equations are Hamiltonian. And McKay and Safman related stability and the idea of collisions of eigenvalues leading to instabilities, and this is all because of the Hamiltonian structure of the problem. All right, so in the case of traveling gravity waves, and these are periodic waves, some of the results, and these are perturbations for waves that are in 1D. Well, there's many contributions from people in this room, Like Vandenbroek studied a lot of numerical solutions for solitary as well as periodic, and they had both gravity and capillary effects. And he looked at even Wilton ripples. And then Dave Nichols, and with some of his work with Ben and others, also used a variety of methods, and some of them were presented looking at the traveling wave solutions and looking at spectral stability, as well as also analytic dependence of the spectrum on the amplitude parameters. And then there's work by Katie and Bernard, and they mostly focused on shallow water instabilities for periodic traveling waves. There's work also that included the effects of surface tension, such as by Keelis and Kim, where they did this for solitary waves and transverse perturbations, and they found that solitary waves are unstable to transverse perturbations. Abelowitz and Hout, who looked at asymptotic series expansions for gravity capillary solitary waves, and also the effects of surface tension on the energy. There's the paper by Akers and Nichols, and I think they have a few. And they look at periodic traveling waves, and they, the one here, they actually looked at deep water, and they looked at both gravity and surface tension. Akers and Gout, I think Ben talked exactly about that result this morning, where he talked about Wilton ripples, but in the case of his toy problem or model equation, however he wants to refer to it, and he actually computed some of the perturbation series for us. And also Tyrone.
Does that include stability?
So no, you're right. He didn't consider stability. He just wrote down, it's true, the title is misleading with the, he just wrote down the expansions. And then there's Tyrone and Choi, who looked at instabilities of Crapper solutions. And actually the important thing to note about that is in their paper, they reference a paper by Hogan. And they say that Hogan found that some things were unstable to superharmonic perturbations, and because their numerics were better, and they're in 2012, they actually found that some of those that were originally thought to be unstable are actually stable because they were able to do better numerics. But then they also looked at subharmonic perturbations and found instabilities that agreed with the paper by Hogan. So that's kind of, maybe, I'm going to talk more about numerics, and that's kind of like a hint at the fact that some things go wrong if your numerics are not good. All right, so let's talk about our formulation, just so we're on the same page. I think many of you have seen some of these slides, and this is reformulations due to Abelowitz, Focasa, Musamani. And I'm assuming one of those people will tell us some stuff about this tomorrow in his Focasa's method, unified transform method for waterways. We might introduce some of it, I'm not sure. But in any case, what we do is, by using the transformation that Zagarov introduced in 1968, what we can set is we can rewrite things in terms of only surface variables. In this case, Q is the potential evaluated at the surface. We can rewrite the kinematic condition, the Bernoulli equation, to give this equation that's only in terms of Q, which is the surface of potential evaluated at the surface eta, as well as etas. So this we'll refer to as the local equation. And then the other thing we can do is we can use Laplace's equation, as well as the boundary conditions, and we can write down another equation only in terms of surface variables, eta and Q. And this, right, so then this we'll refer to as a non-local equation. It's valid for integer values of k. We're on a period of 2 pi, and in the process of transforming the equations, we divided by k, so this is not valid for k equals 0, but all the other integer values of k. So essentially, we can reduce that system, Euler's equations, into a system of 2 equations, one of them local and one of them non-local. So we're looking at traveling waves. So if we switch to the traveling frame of reference by changing our x variable to be x minus ct. So the speed that we're traveling at is speed c. And then we can look at the steady state problem. So setting the time derivatives to 0. That local equation that you saw, we can actually use it to solve qx. And then we can plug that into the non-local equation and get one equation. So now we've reduced that system of 2 equations into one. It's a non-local equation. Once again, it's valid for integer k values because the period is also here, 2 pi. And then for everything, I think, following this, I've highlighted the contributions due to surface tension in red. So this can be done for gravity waves or gravity capillary waves. It doesn't really matter. Surface tension only adds this term. So now we just have one equation that we're solving. And how do we do it? Well, the first thing we did was we did the Stokes expansion for them, so the traditional way, and I'll show that a little later. However, the Stokes expansion, you're summing up terms of order epsilon, and it gets really messy, and it's kind of the talk that Dave Nichols is describing. You know, you have these recursive formulas where your nth term depends on n minus 1 terms, and then it gets kind of messy to solve. So practically, it's not very fun to do. And so what we do instead is we actually use numerical continuation, which uses Newton's method at each point to solve for the actual solution to this one equation. All right, so Stokes expansion.
So is that previous equation 2 equations?
Sorry, this thing?
Is that 2 equations because you have only one complex term, or am I missing something?
It's actually many equations because it's valid for integer k values.
Okay.
Is that, yeah.
Oh, so for each k, there's 2 equations then.
Right, so you can do,
For each kid.
well, there's one.
Where do you see the second one?
There's
Well,
no
'cause
other
it's a
complex term
complex.
in there. It's just the exponential, so it's a sign, the show sign, really.
Oh, I see.
Yeah, so that's true. We don't
Complex
really,
equation.
we only use one of them usually, I think, in practice.
Actually, if you start with even solutions, then you're only going to cosine anyways.
Yeah.
But that's a good question. So then Stokes expansion is just to show you that it does happen. I mean, the usual thing that you do, so expand C in terms of epsilon times some coefficient, eta as well. You can sub it directly right in there, group terms of order epsilon to the n. And you kind of get a recursive relation. So this actually should be Cn minus 1 and eta n. So at each order, you can actually solve it in terms of all the unknowns from the previous orders, and that's the recursive thing. It's really hard. We actually have it explicitly computed, but we don't really know what to do with it because it's really hard to sum up these terms. So maybe if you ever have any input, let us know. But yeah, so explicit formula, but really messy. However, what it does do for us is that it gives us a hint as to what some of the coefficients in front of the terms for eta look like. So for example, if we look at this in infinite depth, so take the limit as h goes to infinity, just take gravity to be 1, we can actually see some of these terms. So C naught will be the starting point of our bifurcation branch. So that's, yeah, so it's G plus sigma G is 1, so 1 plus sigma. C2 is 0, C1 is 0, C3 is 0. But then you also start to see these denominators, 2 sigma minus 1, 3 sigma minus 1, etc. So these expansions can't be valid for sigma is 1 over some integer, and that's exactly the case of Wilton-Erpels. In finite depth, this gets a lot more messy, and so what we end up having is this form of a coefficient multiplying each Fourier coefficient of eta k, and it's equal to some really long expression, but we can explicitly solve for which coefficient of surface tension we have this numerator that multiplies eta k with that, you know, when you solve for eta, it becomes a denominator. So we can solve exactly for which coefficient of surface tension that denominator will blow up. And I think that's really interesting to look at, and that is exactly the concept of resonance. And that's kind of what Ben talked about this morning, except I think the way he set it up was a little different. He was more interested in knowing if he specifies sigma, then for which k that happens. So which integer value. So that was your long and complicated equation this morning, I think. All right. However, if we're looking at non-integer k values, we'll know. So this is valid for k integer. However, if we look at k close to an integer, we might have a small divisor problem. However, things won't blow up. And we can solve for which coefficients of surface tension will get these near resonance. So what we do in our numerics is we fix gravity, the coefficient of gravity, we set it to be 1. Usually for the cases of resonance, the interesting things to look at, because these things happen a lot more evidently in shallow water. So we'll usually fix h to be something shallow like 0.05. And we can solve for sigma for a variety of k values, but k non-integer. All right, and so just a plot of what this looks like. So when we increase the mode, the coefficient of surface tension decreases, so they're inversely proportional to each other, just to show you that explicitly. Okay. So how do we do numerical continuation? Well, recall this equation. So assume in general, in our case, we'll assume that eta looks like a cosine series. We can find that bifurcation point, which is just that g plus sigma times tan h square root of. And we'll assume that eta looks like a cosine, and we plug that in with some small, eta looks like a cosine with some small amplitude. We plug that into the equation, and we use Newton's method and compute the true solution. So that'll get us a point that's just off of the bifurcation branch. Then we scale the solution, plug that in, use Newton's method to iterate, find what the new solution looks like. And what I'll usually show is this plot of amplitude, and I think I actually do something similar to what John Wilkening does, is usually I'll plot on the y-axis the first Fourier coefficient, because for low amplitude waves, the first Fourier coefficient roughly looks like the amplitude of the wave. And then on the x-axis, I plot the wave speed. Okay. And so the regimes that we usually focus on are, I'm going to present the results of Katie's and Bernard's on gravity waves. And then I'll also focus on gravity capillary waves. So first I'll present results that we've published on just what happens with a small coefficient of surface tension. So we're staying away from these resonance phenomena. And then I'll show what happens when we actually increase the coefficient of surface tension to get closer to resonance. And then maybe mention something about resonance solutions. All right, so the way that I usually show these things is, as I mentioned before, here's the bifurcation branch. And then so I plot on the y-axis the first Fourier coefficient. On the x-axis, I plot the wave speed. And then as the blue point goes up, I plot what that solution looks like, the wave profile. It's normalized to 1. And then I plot the Fourier modes. And usually I'll keep the profile for the first, or for at the beginning of the bifurcation branch on there, just so you can compare it the ones further along. And I'll keep something that's in the middle also on there, and then another one at the end. So this is for at the beginning of the bifurcation branch. The one that you'll see stay on there will be in the middle, and then later on. So as I mentioned, this is representing the wave profile. It's normalized to 1, but you can start to see that things, the trough gets higher, and the crest kind of steepens. So this is for deep water. H is 1.5. We took surface tension to be 0. These are just gravity waves. And then this is a plot of the Fourier coefficients. So Fourier mode on the x-axis, and the logarithm, actually, of the Fourier coefficients. And so you can see that for gravity waves, things decay exponentially. So you see them as linear on this log plot. And the way that we do this is that whenever our Fourier modes are above some threshold, we add more Fourier modes. So we actually do this to as much of a precision as we want to make sure that we represent our solutions pretty well. So in any case, the important thing to notice is the Fourier coefficients decay exponentially, and everything looks great. We can do the same thing for shallow water. Once again, these are gravity waves. And then things get nonlinear a lot faster. We can do this with a small coefficient of surface tension. And so this is once again deep water, and things decay exponentially. However, in this case, we actually need more Fourier modes to represent our solution. We can do the same thing for shallow water. It's not super interesting, but it can be done. And then when you compare them qualitatively, gravity and gravity waves with a small coefficient of surface tension look similar. All right, so what happens when you do the near resonant solution? So this is resonance near k is equal to 20. And we solve for what the coefficient of surface tension is. And I showed you that resonance condition. We plug it in there and solve for sigma. So this is shallow water, 0.5. I have fewer points along this branch. And then here's the wave profile. And what you can start to see is that phenomenon that John Wilkening was referring to, is that you start to see these resonances show up. So as we get higher up on the bifurcation branch, all of a sudden you see that the coefficient of the 20th mode starts to get larger than the neighboring ones here. And then later on, you'll start to see the 40th mode show up as well. You can even see that in the wave profiles, that at some point, when they're nonlinear enough, you start to see them, the little resonances appearing, so the harmonics appearing. And then you can play with coefficient of surface tension so that you get closer to the resonant case. And in this case, I think these things come up to be a little steeper. But once again, you see that the 20th Fourier mode becomes prominent in the 40th. And then if I had included more Fourier coefficients, you'll see the 60th, and et cetera. All right, so we can play the same game and switch surface tension so that our resonance is near 10. This is just for illustration purposes. It gets similar, but it gets a little harder because the resonance comes in earlier. And then you can move it and do that again. But yeah, so the important thing to notice about these, so here I guess is the comparison of them. So when we're closer to resonance, these things are a little bit more prominent, but really in here you don't really see too much of a difference, but you see the ripples come in a little bigger. Same for resonance near K, so these are the coefficients of surface tension. And then the important thing to note, and this is kind of something that we did with John Wilkening, and it's that, so on the left you have a plot of Fourier modes at different points along the bifurcation branch, and they're color-coded. So 1 is our initial guess, 2 in green is a little higher, and et cetera. So for when we set K to be 20.5 and compute the surface tension, things look all right, and they look pretty resolved. Here you have some, I think in our case it's less than 10 to the 12 usually, so things are resolved. However, when you get closer to the resonance case, so you set K to be 20.005, what we see is that initially the 20th mode is kind of large, then it goes down, and then it comes back up. And what I noticed is, did you have a question?
I do. K is not the K that was in your Eloise.
No. You're right, it's not that. So that K we fixed because we fixed our period. So that K was 1, and that represents our first mode. But yeah, good question. Any others while I'm actually stop? No. Okay, so what we've noticed is this initial coefficient, the 20th coefficient, low on the bifurcation branch was actually pretty sensitive to what our initial guess was, what our small amplitude solution was. And so
what happened if you put K exactly equal to 20?
It's even more sensitive. I've tried that only recently. It's even more sensitive, and I have a hard time. Yeah. Did you? Yeah.
I haven't tried it.
Yeah. So essentially, that K is really large, decays, and then grows again. When we asked John Wilkening to do this, it seemed like so in blue, that's machine precision for double precision, and it seemed like his started off lower initially, and then they grew the same way that ours did. And then when we asked him to use more modes, still use double precision, this initial growth initial size of the Fourier coefficient, of the 20th Fourier coefficient, was even larger. So including more Fourier modes didn't actually do us any good. The numerics are still, I think, overestimating how large that initial Fourier mode was. And then when we asked him to do this, in quadruple precision, he actually saw that those initial growths, remember, at first they were large, went down, and then back up. Well, he actually didn't see that. In this case, his 20th mode just grew as he was increasing amplitude of the solution. So those are kind of the numerical difficulties we have right now, is that they depend on our initial conditions. Our Fourier modes, our resonant modes might be misrepresented, and they might be too large at the beginning of the bifurcation branch.
Or there could be 3 branches, and you could be picking one sometimes and picking another other times.
But you think that in quadruple precision, we wouldn't, you think that?
It doesn't say that you're wrong. It just says that sometimes in one precision, your initial guess goes to one branch, and another precision, it goes to another branch.
But it seems to then switch maybe, because at first they decay and then they grow.
Solution profiles do the same thing.
Yeah, and so I can even show that later. The solution profiles look the same, but you're right.
You decide that by comparing profiles.
Right.
But in the profiles, it's hard to tell because you can't see that 20th mode very well.
Because we're at 10.15 anyway.
Yeah. All right, so the resonant solutions are going to have even more of a problem. This is a work in progress, and this is kind of where I'm going to ask John and Jean-Marc for their input on maybe how to deal with that. You've kind of presented a toy problem for what you would do for the case of resonance and how you compute some of those coefficients. And so those might provide a better guess for near resonant or resonant solutions. It's hard to do in waterways, what you talked about this morning, and I've tried, and I can get a good initial, what the initial profile looks like for things like if your resonance at k equals 2, you can compute what that looks like. When you have those quartet or quintet or et cetera, those get so messy that it's hard to compute where your initial profile looks like. And I'd like to have some maybe better systematic way of doing it, whether it's numerical or analytical. I ideally like to have something analytical, but anyway.
If k were exactly 20, is that where you get the Wilton's ripple extra branch of solutions?
Yeah.
Okay.
But it's right at the beginning, though, so it's like right at the bottom of the bifurcation branch. So maybe numerically, when we're slightly off, we're not actually at resonance, so maybe it's still okay. But things are going to blow up, though, so I don't know. Anyway. All right, so let me move on to stability. All right, so back to those two equations that we had before we took away the time dependence, because what we like to look at is spectral stability, so we need the time dependence in there again. So we have the local equation. So once again, I've represented the term that has to do with surface tension in red, and we have a non-local equation. So what we're going to do is we're going to perturb our solution with solutions of a different period. But the first thing we have to do is we have to introduce spatial averaging in the non-local equation in order to do that. And then what we're going to say is let's say the velocity potential looks like this Q naught of x, which we've computed from before, plus some small perturbation times Q1 e to the lambda t. So our perturbation will grow like e to the lambda t. Same for eta, the wave profile. And then we're going to use Floquet decomposition. So we set these eta 1s to look like e to the I mu x, where mu is our Floquet parameter. Then since we're working on a periodic domain, we're going to use Fourier decomposition. And then the modes in Fourier series will be represented by m. So it's another integer that we're introducing. And so what we do, if we make all these substitutions and we truncate our system because we can't use infinitely many Fourier modes. So we'll truncate at 2n plus 1, or I guess the size of the system will be 2n plus 1. And so this matrix S, T, and A, and the identity come from the local equation. And U, V, C, and the zero matrix come from the non-local equation. So each of those sub-blocks are n by n. But anyway, and then what we want to solve is this generalized eigenvalue problem. So we're looking for lambda, and lambda will depend on the Floquet parameter, on the Fourier mode of the stability problem, as well as surface tension.
Can that eigenvalue problem be transformed to a nice one? In other words, we know it comes from a variational problem. It was a Lagrangian to start with. So you would expect this to have the left-hand side to be symmetric and the right-hand side to be symmetric. Or you should be able to transform it so that it is symmetric.
I've never tried to transform it.
You mean write it as JL?
Sorry?
Yeah, like in
Right,
a
it's
Hamiltonian
JL.
form, you mean?
Like where L is the Hessian?
Well, that would be a way to go.
So
That's
So
if
use
you're
canonical.
Hamiltonian, but it doesn't have to be that way.
So I think you can do that, and I think it's been done, but it's just not numerically advantageous.
Okay.
I think
yeah.
numerically it's
Numerically,
okay
this
to
is
do
perfectly
this.
fine.
Yeah.
Okay.
Well, numerically, symmetry would be good too if you could.
Yeah.
That's true.
But then
Right.
you double the number of
Safe.
degrees of freedom, I guess.
Yeah, but finding the symmetry in this case is a good
Sure.
Okay. So since the problem is Hamiltonian, we basically don't want the real part of lambda, the
So
eigenvalue.
you're using the Hamiltonian structure anyway.
Yeah, we're using it anyway. But you're right that it's a
Well, actually, we're not using it, we're checking it.
we're check. Well,
Oh, okay.
yeah. Okay. All right. So I'm going to show these. So these are the explicit matrix entries. So they're just long to write, but they're not hard to compute. The only places where surface tension comes into consideration is that matrix S. So that was from the local equation. And they're long, but it's manageable. Wherever you see the C, or I think there's an S somewhere, those are hyperbolic sines, hyperbolic cosines. And, but yeah, everything is in terms of things that we know, eta 0 and q 0. All right, so what we can do is, we can't solve that at all analytically except for flat water. So if we set eta 0 to be 0, and we can actually compute these eigenvalues. And we see that they're purely imaginary, so flat water is spectrally stable, which is good, because it would be not so good if we started from an unstable solution and continued upwards. So how does an instability arise? Well, eigenvalues are continuous with respect to wave amplitude, and I think these guys have done more with that. And as amplitude increases, these eigenvalues may develop some non-zero real part. So that means that if they started to be purely imaginary, they would need to collide, because the problem is Hamiltonian, in order to develop some non-zero real part. And so I've written this collision condition slightly differently than I think McKay and Safman do. I think they write down 2 for even and odd m's. I think you can write it down in this way, not lose anything. So these eigenvalues have a plus or negative sign. They depend on mu, and they depend on the Fourier mode. All right, so the interesting thing too is resonance is a special case of this collision. So if you set mu to be 0, so resonance comes for perturbations that are of the same period as your original wave. What you can do is, that means that if you set mu to be 0, plug that in, then the left-hand side becomes 0. And then the collision condition just becomes whatever was on the right-hand side is equal to 0. When you solve for it, when you solve for sigma, actually using this exact thing, you obtain back that resonance condition that we saw. So that's verified. All right, and so, however, this is only a necessary condition for the loss of stability. And to illustrate this further, imagine you started off, so we'll go back to the beginning, some 2 eigenvalues purely on the imaginary axis, so that's a quadrufold symmetry for the Hamiltonian system. And if they collide, they can go onto the real axis, or this group can collide and they can gain some non-zero real imaginary part, but also have some non-zero real part. But it's not necessary, it's not a sufficient condition because sometimes they can just stay on the imaginary axis.
Now, the motion that you're depicting here is as you move through more and more nonlinear waves.
Yeah, yes, thank you. Yeah, so that's one way, yeah, so that's for us. Our amplitude is that parameter that varies the eigenvalues. Okay, so a few more plots. So if you look at the stability of the trivial solution, so you can actually see what happens for varying depth. And I think in here I fixed the surface tension to be 1 over 90 pi, it's something really small, but it's not for infinite depth. This wouldn't be a Wilton ripple. But what happens is, so here are the plots of an imaginary axis of imaginary part of the eigenvalue versus the depth. You can't read it at all. But basically what this is saying is, I plotted this for different values of m, is that you have this collision for integer m values everywhere, and essentially past a certain point, like 2 point, or I think 3 or something, things kind of look the same. You expect the collision to be in the same area no matter what depth is, as long as depth is something that's 3 or higher. And if you include surface tension, all of these collisions kind of come closer or come further down on the imaginary axis, so you expect them to happen. So the more you increase surface tension, the closer they kind of come down on the imaginary axis. And then you can do the same thing, but plot mu, the flow k parameter where this collision happens, versus h in this case too. And so that McKay and Safman paper mentioned the 2 cases of collision, so they separated into m odd and n even. You can see that's true. They did this for either deep water and infinitely deep water. And then when you include surface tension, you don't just have those 2 cases. You have many different ones depending on what your value of m is.
Is that 1 over 90 times pi?
Yes,
or is it
sorry, it's 1 over 90 times pi.
Oh,
90 pi is in the denominator. I should have put brackets around that. Okay, so let's look at some stability results. So when you actually do these plots, so on the left-hand side I have pure gravity waves. That's the result that Kitty and Bernard published a few years ago. On the right-hand side we have gravity waves with a small coefficient of surface tension. So this is deep water, 1.5. When you zoom out, things kind of look strange, but if you start to zoom in, you see that Benjamin Fear. So I'm just zooming into the origin. So what I plotted is the imaginary part of the real, or the eigenvalue versus the real part. And then you can zoom in further into the origin, you can see that, so I fixed this amplitude, and what you can see is that for gravity waves with a small coefficient of surface tension, that Benjamin fear instability starts to separate a lot sooner than what it would do for the gravity waves. And you can even track this along the bifurcation branch. So here I've plotted those same bifurcation branches with the wave profile. This is for gravity waves, and the only thing I'm focusing on, so this is the complex plane of the Benjamin fear instability. The only thing I'm focusing on is that, and you can see that it grows as you move up the bifurcation branch.
So you're only looking at a superharmonic instability, not
So-
subharmonic.
But we have, I'll show them in a second.
It's Benjamin fear, right? It's subharmonic.
So the fact that you have curves instead of
Yeah, so that's
the
the,
fact that you have discrete approximations to curves as opposed to just isolated eigenvalues means you're doing subharmonic because you're going through overflow K parameters.
all right, so you can do the same thing for non-zero surface tension. And then you can look at shallow water, and this is probably even more obvious that these are subharmonic because these are, I didn't plot the mu versus eigenvalue plane, but without surface tension, with surface tension, you can zoom into one of these. This is just the largest bubble that I've zoomed into. And you see that it's just a little larger for non-zero surface tension, and it's moved down the imaginary axis. So as expected from that collision condition, that's exactly what we thought would happen, and numerically you see it as well. You can zoom into the center, and you still see little bubbles. This is not the Benjamin fear instability. It's just bubbles that are close to the origin. And then they're more prominent in the case where you have a small coefficient of surface tension. And you can track these instabilities as well as you move up the bifurcation branch, and you see that they start off kind of lower on the imaginary axis and they move up and grow. You can do the same thing with small coefficient of surface tension, where I've actually apparently put in the brackets explicitly. And then, so these are just a couple plots that we did for exactly tracking those largest bubble instability, and this is the second largest. And so the actually interesting thing to do there is it's easier to start off with a larger amplitude wave because it's hard to figure out where those Fourier parameters are for the instabilities. So if you start with something that's a lot more nonlinear, those things are more prominent. And what we end up doing is actually we track them backwards. So we go from the largest to the smallest. And so these darker lines represent the center of them, and the lighter lines represent the outer parts of them. And then you see that they actually come back to exactly those values that we computed for the collisions. So that's as predicted, so those things are there. You can track the growth rates, so that's the maximum real part of the eigenvalue versus the amplitude as well, and we do this numerically. This isn't analytic results, this is numerics. And then the other thing too that is in the paper with Bernard and Katie is that you can see that for gravity waves, and this is similar for gravity and capillary, but the Benjamin fear instability, it's present for deep water, but if you look at a graph of a particular amplitude of wave, you can actually see that despite the fact that Benjamin fear instability, which is the dotted line, appears, the dominant instability in that region for that fixed amplitude is still those bubble instabilities, those subharmonic things that we saw. And so, for example, for that fixed amplitude, in this region, the dominant instability is the bubble one, not actually Benjamin fear, which I think is kind of interesting. And I think that. All right, so we can do similar things for our near resonant solutions. And so if we look at different surface tension for shallow waves, we can see that, zoom out, nothing really that interesting, but something close to the origin appears. And so this is, we zoomed into the origin. So these are the shallow water instabilities. They look like bubbles. And then you can move up. This is a more nonlinear solution, and you start to see them more prominently. So these things are bubbles as well. They just haven't been fully computed. And you see that just before you get to that case where you see those ripples, you start to see these secondary bubbles as well. So we can do that too. However, this is that note about the numerics. If you have a solution, and so, for example, on the left-hand side, we have the double precision solution that we said wasn't very, very good. But on the right-hand side, we have John's quadruple precision solution. And we look at the wave profiles, they look almost identical. You don't see the difference between double and quadruple. This is still very, very light. I guess you'll have to take my word for the fact that they look really similar.
Do they have ripples in the top? Or?
These guys don't yet.
They don't yet.
These guys, you don't see them yet, but that mode is already in there. It's already present in there. And then when you look at the stability results, when you look at the double precision stability results that I did way before, all my stability results look kind of weird. So the scales on the horizontal and vertical axis for the two figures are different. But basically, the important thing to note is for the double precision solutions, we had these larger instabilities that weren't in the shape of anything that I've seen before, and I didn't know what to do with them. But then when you do the stability analysis for the quadruple precision solutions that John presented us with, things looked better. They looked like the bubbles that we expected that we've seen before as well. So the instabilities were way smaller. I think this is 10 to the minus 7. This scale is 10 to the minus 5.
Are these reasonably large amplitude waves? Or?
These guys, I think, judging by the nonlinearity of them, they're reasonably large. So the way that I always look at reasonably large in case of surface tension, it's a little harder to define, I think, for me, because I don't really know what my comparison is.
Like conoidal.
They look like them.
Yeah, exactly. So those are,
So what is the steepness then? 0.5, 0.7?
in terms of gravity capillary waves?
Yeah.
I'm not actually sure what the steepest would be. Do you know how to compute that?
So what's the
For gravity capillary waves, what's the steepest wave that you could compare it to? Or
well, when you plot the thing, it's not monotonic, so it's hard to.
right. So I don't.
But you get an order of magnitude. I mean, 0.8, I know you can have steepness of 0.8 from gravity capillaries.
But it's hard, right? Because its steepness as it relates to depth.
I know Krapper's solution is about 0.8.
Yeah, that's why I called it.
0.78.
Yeah.
He just wants to know the maximum displacement divided by the wavelength.
Yeah, I don't know what
It's
they
just a
are.
slope, you know, steepness is slope, yeah, it's just
Right.
eta x.
So I mean, in this case, I have it. It's
And
I
would you
don't
normalize
really know what it is.
to
I don't
one?
have it actually. I normalized it. That's a good point. I always look at steepness based on my nonlinearity. I always say, oh, this is pretty nonlinear instead of. Anyway, that's the way I do it. So that's a good question. I'm not sure. I don't know. I don't think it's 0.8. I think it's way smaller than that for this case. All right, so let me conclude. So basically what I've shown you guys is that all the solutions that we've computed in all the different regimes, including ones that I don't know, the resident ones, for periodic water waves traveling at a constant speed c are spectrally unstable. They're spectrally unstable to particular perturbations because they're unstable in the particular regimes of the flow K parameter, but they're all unstable. And so you see these instabilities in shallow water as well as you see those Benjamin Fear, but you also see those bubble instabilities in shallow water as well as deep water. And then in some cases, they actually even dominate the Benjamin Fear instability that I showed you. And then we can also track these stabilities as a function of amplitude of the wave. And the thing that I would like to do is actually get more results in the case of larger surface tension. And hopefully with people's help, I can actually accomplish that here. Yes?
Can you use this formulation to calculate overturning waves? Limiting, no?
I can't do our stuff. Because our stuff is symmetric.
There is a limit of how much you can put the surface tension and how strong can be.
Sorry? How? Yeah. Yeah.
Just X is your spatial coordinate. So
Yeah, so I don't.
Yeah.
But your formulation assumes that eta is a function of x.
Yes.
Yeah.
Yeah.
So it cannot overturn.
Yes, but that
So
formula
ours
can
is
be modified
symmetric.
to for a parametric surface if you wanted to. Yeah.
I think questions about that were vorticity.
For vorticity, yeah.
Overhanging purposes.
So what happened to the type 2 instability?
The type, I think they could just be grouped into one, the type 1 and type 2. I think it, is that what you're saying? The type 1, type 2, I think they
Type
just
1
are
is
grouped into
Benjamin
one.
Fair, and type 2 is the 5-wave.
But it's more than that. There's more than that in
all the odd
both.
ones are one type and all the
Yeah,
other ones
yeah,
are the other.
So can you, did you distinguish or?
I didn't distinguish because to me, I just grouped them into the same
And
thing. It
Once
doesn't
you're at
really
surface
matter.
tension, they don't collapse to two flow K
Yeah,
parameters,
exactly.
so it
So
doesn't really
that's-
make sense to classify
So,
them that
so
way.
So that's
can I
this
ask
graph.
you now, why are you guys all including surface tension at the moment? Only, and not viscosity? Why are you only doing, is there some practical need why we have to include surface tension?
Well, it's the full.
It's the opposite. You're studying traveling waves, so you can't include viscosity.
Well, yeah, you can, of course.
Not in confined traveling waves.
You apply a bit of pressure. That's right.
Ocean waves. I mean,
Yeah, I mean, I'm talking about the real case. Because the things, because bubble instability is very nice. But I think when you add some viscosity, it might look a bit different, yeah? I'm saying this in a polite way.
A reference for that is Fedorov and Melville. They wrote a paper in 1998
Yeah.
that included surface tension, viscosity, and forcing.
Yeah.
So.
But one answer to your question is, as far as we know,
Yeah.
there was no study of the stability of the periodic gravity capillary waves.
Yeah, there is.
A full spectral stability analysis?
Was it not challenged?
Not sure about that, but I know there is. It's actually published in the Wave Motion back in '70s.
How was the stability studied?
Well, it was just the extension of what Benjamin Spear did, with the inclusion of surface tension on deep and shallow water.
So most numerical studies did periodic or harmonic or super periodic.
perturbations. Yeah.
Super harmonic.
Super harmonic.
Going through the entire range of Fouquet parameters brings in subharmonic, which that's why you get these curves. Otherwise, you're just going to get some of the few eigenvalues. So, for instance, if you look in shallow water, gravity waves are stable if you only do periodic perturbations.
Mm-hmm.
So the interesting part comes in when you do subharmonic perturbation, then you find out that even waves in shallow water of all amplitudes are unstable.
Or all amplitudes.
Yeah,
But
Yeah,
you have to
well,
do subharmonic.
and surface tension.
Okay, so this.
Well, you don't have to
No,
do
it's
surface, you have to
gravity.
gravity as well. It's for gravity and,
Shallow water waves, just gravity waves.
Absolutely.
yeah.
Put the graph
Subharmonic.
up again, Olga.
That's really already in mechanics happening.
Yeah. For these collisions, and then, I mean, these guys.
Yeah, but these
So
are
this is-
higher order instabilities. This is type 2.
They're instabilities.
Yeah. Yeah, but I mean, we order things in nature, you know. If you have, say, 5-wave or 6-wave interaction, it's a higher order interaction.
But there's no Benjamin Fear here. This is shallow water.
Yeah. But can I just explain something?
Please.
No. You know, the steep, in practice, steepness is quite small for the ocean. Yeah, if we have steepness of 0.1, then it's a quite big deal. So all those instabilities, the Benjamin Fear instability involves, if you look at the spectrum, it involves action density to the third power. If you go to the next interaction, you get an additional action density, and since the order of magnitude of the action density is steepness squared, you know, the effects will rapidly disappear. So in practice, we just stop there.
You're absolutely right. The growth rate of these instabilities, of the bubble instabilities, is usually quite small.
Yeah.
But there are instabilities.
Yeah.
In extreme turbulence, like hurricanes and so on, we do get a wave of steepness of 0.3 in the ocean.
Yes. Okay, but
How many are taking
that's sort of the same as freak waves when we.
No, there is.
Excuse me, maybe a question. You talked about Benjamin Fehr instability, which is correct. Benjamin Fehr instability is instability of modulations, correct? Therefore, you have one small period and one very big period. But your analysis of linear stability are related to the perturbation of the same period or not?
No, they're not.
No, therefore you consider complete spectral
Yeah.
theory with block functions.
Yeah.
Yes.
With all depths, and how you numerically manage to do this.
How do we do it numerically?
Yes.
Um,
Complicated stuff.
it's not so
Thank
bad.
you.
But did you want me to show it, or you're
Just show
saying
the-
it's okay?
just show the focus.
I don't know where. There it is. I mean, right. I mean, I guess what we do is we end up linearizing,
Yes,
and then we plug all of this,
yes.
and we just get our
That's
generalized
the
eigenvalue.
problem,
Yeah.
yes.
So then we
On
vary.
the real line,
So then
the
we.
equation is defined on the real
Yeah,
line.
yeah.
In L2 of R. Yes?
Okay.
And then you consider the complete.
Right. So what we do is we vary a lot of that Fouquet or block parameter, and we compute this for each one of them.
It's like in physics and solids, but in physics and solids it's considered like a problem.
But it is here too.
So why don't you get continuous spectrum? I guess that was my question. You do.
It's all
says not
continuous
all.
spectrum.
It is
We have
continuous.
location.
Yeah, it's
Yeah.
there. I mean, I can only. Yeah.
Okay, let's thank Olga again, and now we call.